So, hello everyone. Today we are going to deep dive into binary search trees. Before starting, I would like to put forward two simple word jumble of the binary search tree, which is binary search plus tree and binary tree plus search. These are very simple words that sum up the meaning and the concept of it. Binary search plus tree is just the tree that uses binary search as a base algorithm, or binary tree plus search, or it's like a binary that is used for search. Both of these concepts into the same thing, which you'll understand at the end of this video. And this is just that it will help you to understand the concept very clearly, even though the intuition of this video is going to be enough for you to actually grasp the concepts. So a good question before starting would be, why do we need a binary search tree? Are the data structures that we have not enough to get the work done? So let's start with it. Why do we need a binary search tree in the first place? Why do we need it? We have an unsorted array, we have a linked list. So why do we need a binary search tree? The problem is, in an unsorted array, if you want to find an element, you have to traverse through the whole array, and that's going to be O of n time complexity. And since there's no order, you can't predict or you can't take any shortcuts in searching. Similar with the linked list, you have to traverse the whole linked list and walk through every node to find if the value that you're trying to find is actually exists or not. The only difference is that between is the same space complexity in linked list and unsorted array. Even though that's not the concept of this video, that's just a difference that you have to note. And the one difference that will make is, if you sort this array, you can use binary search on this, and that's a great intuition to start with. The sorted array, if you sort this array 925761 to, it will become 12567 So if finding an unsorted array is way easier, and it's way time saving. If I'm at a node 6 and I'm trying to find 2, then I'm sure that since 2 is less than 6, it's going to be in the left sub array. And if I'm trying to find 9 standing at 6, since it's greater than 6, I'm sure that it will fall in the right sub array. So this will bring down the complexity of logn. So we got a sorted array, we can search in this, and it gives a great time complexity of logn. But what's the problem? The important problem is that it comes with a costly operations, which are insertion and deletion. If you want to insert an element into this sorted array, you have to find the right position and you have to move elements right to the index where it needs to be inserted and move all of them by a block 1. And deletion has a similar fate. When you delete an element, the elements to the right of the subarray have to move by a position 1 to the left side, so that the array stays contiguous and ordered. So these are costly operations that we can't afford at a large data. So O of n should also be diluted. So if you can observe closely, the problem over here is that insertion and deletion affect all the elements in the array. When the 3 comes in, it affects all the elements, and every element has to move so that it can make space or cover the space that has been left or occupied by the incoming elements or outgoing elements. So we got the intuition of why this is happening. So can we find a data structure that actually reduces the effect of insertion and deletion on the other elements? So the question comes this: do we have a data structure in which insertion and deletion do not affect every element? Yep, there is a data structure, and that's the tree. The tree, any operation or performed on a node or an element only affects its ancestors and predecessors. So we found a data structure, that's good, and we have a base algorithm, binary search, for searching. So how could we merge these two concepts of binary search in a tree? And to actually understand it very clearly, we'll get down to the basics and look at binary search and how it's being implemented. So let's consider this sorted array 1 2 5 6 7 9, which I think we have been observing for a long time. So let's find 6 in this array. We'll keep L at 0, high at 5. So the mid comes out to be 2, which is 5, and we ask the question, is 6 less than 5 or greater than 5? So 6 is greater than 5, so it has to be in the right sum array of 5. So our search space becomes the right sub array of 5, which is 6, 7, 9. We ask the same question to the mid element 7, and it says the ref sub array is where it needs to be found. So we come down to a single element and we ask the question, is this the element that we are trying to find? And if it's yes, we found our element, and if not, then the element doesn't exist in the sorted in the array. So the concept I'm trying to teach you or show you over here is the point I'm trying to sell you is, in binary search you always split the space around the mid element. So the mid element is 5 over here, and then you split it, and it's 7, you split it on 7, and then there is no splitting. So yeah, so this is how you do. You split at the middle, and the intuition is, if I take 5 as my root node and this as my, and the right subarray or the left subarray of 5 as my left child or left subtree, the right subarray as my right subtree, and then continue the same. You take 7 as my root of the right subtree of 5, and then recursively do the same steps on left and right. I think I'll build a search tree that actually uses binary search. So we'll not go deep dive, we just stick to the what we got an idea of. Let's take 5 as my root node and elements less than 5 to be the left subtree, and the elements greater than 5 as my right subtree. And if I do the same thing to the right and left subtree, taking this as my node, root node of the right subtree, 7 being the node, root node of the right subtree, I can do this as 6 will be my left child and 9 will be my right child. So that's how it is. And elements less than 5, this will be my mid, so this will be my root node of the left subtree, and this 2 will going to be my the right child of or the right subtree. So we have kind of grasped this intuition of it. So we are trying to split at the middle, and then we are trying to construct this using the binary search. Let's check if we are falling on the same page. Is our tree that we build is acting similarly as we intended? Let's see, if I'm trying to search 5 and I'm trying to search 6, I'll ask this question to the 5, is 6 greater than 5 or less than 5? It's greater than 5, so we go to the right subtree and I ask the same question, is 6 greater than this root or less than this root? So it's less than, so I come down here and find 6. The similar steps have been captured in the binary search on a sorted array, so our tree is working fine. And the insertion and deletions are the functions that we are very fond of, that how are they gonna occur in our search tree, and that are actual concerns of our as in the array. So we're going to find, first we'll start basic. We just saw how we are going to find the simple points to remember are that right subtree the right subtree of a node are always going to be greater than the node value, and the values of the left subtree are always going to be less than the value of the node. So this is a simple point. Now if I want to find 9, I'll ask a simple question, is 5 or is 9 greater than 5 or less than 5? It's greater than 5, so I'm going to the right subtree of 5 and I ask the same question to 7, is 9 greater than 7 or less than 7? It's greater than 9, is greater than 7, so I go to the right subtree of 7, I'll find 9 here. But what if I want to find 10? So I'll start the same here. 10 is greater than 5, I come down here, and 10 is greater than 7, I come down here, and 9, and 10 is also greater than 9, but there's no right child, so I stop. So 10 is not in my binary search tree, so what do I do? But I found an important conclusion that if 10 has to be there, then that could be over here, right? And then that should be over here. And if I have to insert that, then this is the right place to insert. So you can use this information and compute where the elements need to be inserted. So if I want to insert 10, I'll get this 9 pointer, and then I'll ask, is 10 greater than 9? Then if it's greater, then I'll keep 10 as the right child of 9, and if it's less than, then I'll keep as left child. If let's say we have to find 8, then I'm going to ask the same questions. Is 8 greater than 5? Yes. Is 8 greater than 7? Yes. And is 8 less than or greater than 9? Oh, it's less than 9, so this is where it should be. I'll return this, and when I get this node 9, I'll ask the question, is 8 less than 9? Yes. So then I'll put it as the left child. The concept over here is you get the parent node and you ask if it's the value is less than or greater than, and depending on it, you'll keep it as its left child or its right child. That's how it's going to be. And remember that every insertion that happens in a binary search tree will always occur at the leaf nodes. Right? These are the easy parts. Now let's get to the part where it's getting interesting, the deletion part of a binary search tree. When you have a leaf node, it's easy to delete. If I'm trying to delete 27, I can delete 27, or if I'm trying to delete 15, I can delete 15. The concept of the binary search tree still holds because the properties of the other nodes doesn't change. But if I have to delete a node with a single child, right? If I have to delete 35, right? If I have to delete 35, I delete 35, but someone has to take the place of 35, right? So someone has to take the place of 35. I think this works. Yeah, someone has to take the place of 35. What could take the place of 35? So 30, can 30 take the place of 35? So it's a good question. And if I promote 30 over here, can the binary search tree property still hold? So all of these nodes are greater than 25, and if I 30, 27, all of these are greater than 35. And if I promote this, the 30, 27, since this already holds a binary search tree property, it's not going to be affected because of its ancestor. So if I move it up, this part of the subtree is still going to be same. It's going to handle its properties. And 25, since 30 is greater than 25, it's still going to hold because every element right side of the 25 are always greater than 25. So any element of this subtree put here will still satisfy for the 25. So if I promote the one child 30 to here, the binary search tree property holds. And this is a keynote point that you have to make, that if you're going to delete an element with a single child, then you can just promote its child to take the position of the parent node that is being deleted. And if it has a two child, then I would convince you to take the minimum of the right child or right subtree and promote it to the deleted node position. So why is this better? So I'll walk you through. If I want to delete 75, I'll go to the right subtree, which is this, and get the minimum value of it. And before this, I'll try to make you believe or try to sell you a fact of this. Actually, let's go up here and look at this. So the array actually over here is 1, 2, 5, 6, 7, and 9, right? So look how the element here is 1. How should I? Yeah. The next element of 5 is 6, right? The leftmost element of the right child, right? And the next element that is greater than 7 is the leftmost element of the right child, since there is only one element, then this is it. And 1, the next element greater than 1 is the it's going to be 2, the leftmost element of the right child. Why is this happening? This is a key property to note. And why is this happening? So now we have this array. You know that the right child always considers the value greater than the node, right? And the left child considers all the values less than the node. And if I go to the right subtree and traverse along the child, and if I keep going left child, so I'll get to a point where I'll find the element that is just greater than 5 or just greater than the root node. So here you'll end up here. How do you do, like how it's working? So this is how I'm here, and if I if I'm at 5, and if I keep going to, first I'll go to the right subtree, this is over here, and if I keep going to the left, then this is where I end up. The just next element of the node where you have started. If you go, this is where the node where I've started, and let's not take the mid node. Just for example, I'll take the 2. This is my right subtree now, and this is the mid, and since I started, this is the right subtree, and now I have to keep going left, and the left is just the element. I'll always end up at the element that is just beside the element that I'm trying to search, right? If I take 1, this is going to be my right subtree, right? This is just, I'll assume that there are elements, that the same number of elements on the right side, so you don't get confused. And this is going to be my mid, and if I go to, this is the right subtree, right? And if I have to go to the left of this is where it is, and this is the mid of it, and this is where you actually end up. You always end up with the element that is just beside the node you have started searching from. If you go to the right subtree and if you keep moving left, then you'll end up with an element that is just greater than or just beside this. And if you pop up this element, this has to take its place, right? So that's what I'm trying to sell. If you go to the right and you pick the element that is just greater than this value that you're trying to delete, and just replace it with it, the binary tree property holds. And I'm going to prove you or convince you that the tree property actually holds. And just say, if I remove this 75 and keep 80, what are getting affected, right? What are getting affected? So the first thing, let's check the right subtree. Since this is the minimum value of the right subtree, all the elements that are in this subtree are greater than 80, right? Greater than the element we have replaced. So the right subtree still holds, since this is the minimum value of the right subtree and we have replaced with it. That means all the elements in the right subtree are still greater than this value. Let's come to the left subtree. So the element we have replaced with is greater than the element which was here. Since all these elements are greater than 75, then all these elements will for sure be greater. All these elements are less than 75, so for sure all these elements will be less than 80, since it's actually greater than 75. So any element that you replace, you have to replace, you are actually asked, or I'm trying to convince you to replace with the rightmost or leftmost element of the right subtree, right? There's another way of doing this, which is you take the maximum value of the left subtree, which is, you can watch that 60 is the maximum value, and if you replace it with 60, the tree still holds, because all of these elements in the left subtree are less than this, so all of these elements will still stay less than 60, and all of the elements this side are obviously greater, because this value is actually less than the value of the node. But there's a problem with this, because every time I delete from the left subtree, it's not going to be the node. It's not going to be a leaf node. And when I actually delete, I keep going down until I hit the leaf node. So in this case, I'm guaranteed that I'll actually end up with leaf node. But in this case, when I move on the left side, I'm not guaranteed that I'll end up with a leaf node. So if I replace with 60, right? If I replace with 60, this is going to be 60, but this 60 has to be filled which needs to be filled with 55, and if this tree is actually larger, then there might be another chance that if you keep moving left, then you'll have to make a lot of replacements. So it's always suggested that you pick the element that is the minimum value of the right subtree or the leftmost element of the right subtree. This is usually called the leftmost element of the right subtree is in order successor, right? And the maximum value of the leftmost subtree is called in order predecessor, right? Since we grasp the concept, you can just play around and find out how these are actually working. These are just intuition for you, and if I have to construct a tree from the given information, let's do some examples so we get our hands dirty. And we are starting with root 50, right? Root 50. Okay, this is not good. So we are starting with root 50, right? And then we're going to insert 25. Since 25 is less than 50, it's going to be left, and there's no point, there's no node over here. So this is going to be filled with 25, and 75 similarly it's going to be right. Since this is a null pointer, we'll put 75 over here. There's no more comparison needed. And 30 is less than 50 and it's greater than 25, so it comes actually here. And 80, so it's 80 is greater than 50 and actually greater than 75 too, so 80 comes over here. And then you have 15, which is less than 50 and less than 25, which comes over here, right? And then there's 65, which is greater than 50 and less than 75. 65 actually comes here. This looks like a beautiful binary search tree, and it actually is. So everything, every element searched here is actually going to take O of logn time, but not all trees that you make up this way are actually going to be beautiful. Let's see this example. 50 is going to a root node, and we're going to insert 40 is inserted, and then you get 45, which is less than 50 and greater than 40. So this is where it should be, and we're going to insert 47, less than 50, greater than 40 and greater than 47, or 45. This is where 47 should be. And 49 similarly, 50 less than 50, greater than 40, greater than 45 and greater than 49. So this is where 49 should be. And you can clearly see that in this example we are actually traversing through all the nodes to find the element whatever you're looking for. So this is actually not O of log of n, this is actually O of log n. So the time complexities, you shouldn't be fooled, because this tree is actually not balanced. This is just a linked list. So this is the worst case that you might get, in which the whole binary search tree converts to a linked list. So how can we avoid this? How can we keep the tree always balanced so that every time it takes a O of log n observation? So this is the concept where we build AVL trees, which are pretty useful for a lot of insertion and operations happening in a binary search tree. So we will see about AVL trees and the implementation of binary search trees in a code in the next video. Until then, take care. Bye bye.